Hello and welcome. In this video, we're going to go over how to solve these two homework problems. These problems are covering topics in astronomy that are focused on light. Problem 1 is all about some fundamental properties of light. In fact, a lot of different laws that are interrelated that all apply to light, all set up in one situation with a star kind of as the focus point, and we can solve for a lot of different quantities. So it's a kind of a neat showcase of using many formulas related to light. So that's number 1. 2 is also about light, but more indirectly. It does also mention a wavelength, so certainly we have that important physical quantity from the electromagnetic spectrum that's shared by both questions. But number 2 focuses on telescopes and on an equation that actually is specific to telescopes. This has to do with the basically the limit of how much resolution is possible with a perfect lens and perfect magnification. What can you achieve? Because one of the things that telescopes do is magnification. All right. They also collect more light, which is a very important aspect of them. But in addition to that, they magnify. And there's a limit to how much a telescope can magnify an image, especially as it's dependent on the wavelength. So in this case, we want to look at a light of wavelength 400 nanometers in question 2. That's visible light. So the idea is this is a visible light telescope looking at light that is on the shorter end of the spectrum, so bluish light. And in addition, for 2, we have to use the angular size formula, okay? So it's not mentioned in the body of the problem. This is a topic that we saw previously that is covered in previous ideas in astronomy, but it is an important formula and you cannot solve the problem without it. So I'll go over how to use it in just a minute when I do talk about problem number 2. All right, so let's get into the first one, which is just a series of equations. Mostly we're just going to plug in the quantities that are given into the equations given. There's very little moving around variables or solving for anything. All right, so actually let's do number 1. So we're first told there's some temperature. I won't use the temperature that you're going to be solving, so let's just consider another value. What if there's a star that has a temperature of 11,000 Kelvin on its surface? Well, temperature that an object glows at is directly related to the peak color light that they produce, all right, which is represented by its peak wavelength in this formula right here, known as Wiens Law. So what we want to do then is solve for the peak wavelength for a star of this temperature. The temperature that I'm using in the example here, or in the help video, which is 11,000 Kelvin instead of 6,120 Kelvin, which you'll be using. All right, so the formula basically allows us to plug in the temperature and get a wavelength out. Okay, so if you look, it's got a constant, 2898, and that constant has units of distance per, or rather distance times temperature. So it's distance temperature. And specifically with the numerical value given, it's micrometers times Kelvin. Okay, Kelvin is how we measure temperature. At very cold things in the universe are close to 0 Kelvin, and 0 Kelvin is absolute 0. All right, so it is the temperature scale used in astronomy. It's not too different from Celsius, especially on large values. You'll find that they are similar, but do make sure to use all the values in Kelvin. All right, and then you can see in the formula that in the denominator is the input. That's where we actually place the temperature. The given temperature, okay, the variable we place in is the 11,000. We don't have to convert it at all. All right, so then we can make that calculation. So if we have 2898 divided by 11,000, let's see. All right. Well, I've had easy access to a calculator, so actually I do. Hold on. There we go. Sorry for the interruption. There we are. Okay, so we wanted to calculate this. I wanted to show you the type of value that you would get for this calculation. All right, so I'm going to find the peak wavelength right now. So I'll put in the 0.98, and then I'll divide by the 11,000. Okay, so you can see my value is 0.263. Okay, so 0.263. What are the units going to be? Well, the Kelvin canceled, so the units are going to be micrometers. Notice, though, that in the body of the problem, I ask you to give the answer in nanometers. So we just have to do one last conversion and convert those micrometers over to nanometers. All right. Well, what is the conversion? Well, there's 1,000 nanometers in every micrometer. So we move the decimal over 3 to the right. So in this case, it would become 263 nanometers. Okay. So the peak wavelength for this star is actually in the ultraviolet, which is typical of the hottest stars in the universe and that are in our own galaxy, for example. So it's a very hot and exotic type of star to imagine, where it actually shines in the ultraviolet. Okay, so moving on to just another question about light. We are asked, what is the frequency of this peak light? Okay, so we found its wavelength, but we need to find its frequency. For that, we have this simple relationship between wavelength, frequency, and the speed of light. All right, so wavelength of some type of light, any type of light from microwaves to radio waves, invisible light, everything in between, X-rays. Over here, F is the frequency, the number of times that type of light oscillates up and down, bounces up and down per second. And C is always the same number. C is just a constant. It's one of those fundamental constants that we use over and over again. So let's make the calculation here. So we know that C equals lambda F. And we know lambda now because lambda is lambda peak. So if I solve for F, I'm just going to have C over lambda. All right. So we can go over here and we know that this value that we have is essentially equal to lambda, the one that I calculated. However, we want it to be in meters when we put it in this formula. If we leave it in nanometers or even micrometers, we'll not get the right frequency, or in other words, we'll get the frequency with the wrong units. It won't be in hertz, it'll be in kilohertz or millihertz or something, okay? So what we need to do is take this answer and convert it to meters. And we know it's going to be on the hundreds to the -9, or we can just use the existing decimal I have in the calculator and take that to the -6. So let's just do that. It's the easier thing to do. So I'm going to take my previous calculation and then raise that to the -6 power. Okay, I'll show you a little bit larger there. All right, so you can see what I've done, just multiplying by 10 to the -6. And now that has given me my value in, well, meters, okay? Now, it doesn't maybe look like nanometers because you see the -7, but that's just because the calculator will always give it in proper scientific notation with only one number on the left of the decimal place. Now, I'm going to name this variable, and we're going to name it, we can't name it lambda, but we'll name it L. See, there we go, equals that. So now when I make another calculation, the calculator here, Desmos, will be able to use that as basically a constant, use it as a variable, and plug it into something else, which is what I want to do on the very next line. Because I want to find the frequency. All right, I'll go ahead and call the frequency F because I'm going to need it next. So we'll do that. Okay, and then I'm going to have the speed of light, okay, which I could have saved as its own constant, but we'll just put it in. That's 3 times 10 to the 8, all right, in meters per second. All right, and then I'm simply going to divide by L. Go back to that keyboard, and there we go. We got it. We have our value of frequency. Okay, so we have our number for the oscillations per second, which is hertz, as 1.14 times 10 to the 15 hertz. Okay, so we've gotten two of our values so far, two of our answers for part A and B, respectively. Okay, yeah, it's a really big number. So basically, visible light or near visible light, in this case, this is even faster than visible light, is oscillating up and down hundreds of trillions of times per second. So these are very, very fast waves. That's in contrast to radio waves that only oscillate a few thousand times per second. All right, so in part C, we're asked to find the energy per photon of the light that is emitted by this star. Okay, so light breaks down into tiny little pieces, particles called photons, the smallest peak of light or smallest piece of light. And every one of those carry a little bit of energy. And we often use that value, energy per photon, to compare between how much energy, say, an X-ray has to a 1 photon of red light, visible light. Because then you can really see that one type of light maybe just packs a bigger punch, has a lot more energy. All right, the values are going to be that we're going to get are going to be in joules, which is the standard for all energy values. Okay, every time we talk about the energy of a sun or a star or a supernova, it's always going to be in joules. Whenever we talk about power, it's always going to be in watts. All right, so let's then take a look at the formula we're using. It's simply this one, right? We're going to plug in the value of F that we solved for from part B, and we're going to plug in H, which is just a constant of the universe, actually very similar to the speed of light and the gravitational constant. And it's one of the big three, and it is called Planck's constant. I say it's one of the big three because really physicists suspect that these three constants define every other parameter in the universe. Whether there are other constants as well that sort of fine-tune the universe, perhaps there are, and they just have not been discovered. So let's plug in the numbers. So we want to find the energy, and this is a tiny packet of energy. It's the energy of 1 photon. There are trillions and trillions of photons in any even small amount of light, like a tiny little glowing LED is still emitting trillions upon trillions of photons. They're very, very small. But on the other hand, the human eye the brain can detect can detect single photons. So it's kind of amazing the whole scale of how we interact with light. But to continue with our example, let's plug in some numbers. Okay, so we have that constant, which was 6.626 times 10 to the negative 34 joule seconds. Okay, Planck's constant, just copying down that value right up here. All right, and then we'll multiply by the frequency of light that we solved for above. And that's going to give us our units of energy. Okay, so let's go ahead and plug those numbers in. So we'll call this E. I don't think we'll need this number again, but just in case. All right, and then we'll have our 6.626, okay, times 10 to the negative 34. All right, and then we'll multiply that by and we won't round this value, we'll just use the value from above by multiplying it by what we saved in the calculator as F. You'll get much better numbers that way because you are, what was I going to say? I just saw the error symbol there and got distracted. But you won't be making any rounding errors, which can really throw off your numbers. Okay, so it's an easy way just to get much more accurate answers at the end when you do a series of calculations. So, I see. All right. Well, then I see. I can't redefine E. Okay. There we go. I'd have to go up and delete my previous constant that I called E somewhere up above. But anyway, or perhaps E is already used actually because it's I bet it's E as in an exponential. But anyway, not relevant to this problem. So let's write down our value. So 7.55 times 10 to the negative 19, all right, and those would be joules, okay? Incidentally, this is actually close to what's a unit of energy called an electron volt. So when people talk about this amount of energy, they would say that this is about 4 electron volts. So there's actually a good way to talk about this amount of energy because it's a common type of energy and not worry about those giant exponents. Or, well, big numbers, but tiny, tiny values. Okay, so we got the last two parts. These are ones I definitely want to show you how to use these equations, okay? So we have an equation here for part D, where we're going to use this luminosity equation, all right? So luminosity is power. So the value we're going to get right here is going to be in watts. So let's take a look and plug in some of those numbers. So A, B, C, D. Okay, so we have value for luminosity, it'll be 4 pi squared, no, there's 4 pi, and then times the radius of the star that will be given in the problem. In this case, the case you'll be solving for, it's 300,000 kilometers. You'll need to convert that to meters. I'll do a slightly larger star, so we'll do 5.0, and we'll have times 10 to the 8 meters, okay? And that is going to be squared. So the idea there is that if it's, for example, up here, if it's 300,000 kilometers, that then what we want to do is, oh no, there should be another zero there. But what we need to do is we need to convert that over to meters, which means we're multiplying by a factor of 10 to the 3. So instead of having 3 times 10 to the 5, it becomes 3 times 10 to the 8 when you convert from kilometers to meters, okay? So this here should have another 0. All right, so I will fix that if you look at this after you see this video. If you go back to the Canvas page or look at this homework, you'll see that updated, but that's the fix on the typo. But regardless, that would be 3 times 10 to the 8. In this case, I'll plug in 5 times 10 to the 8. All right, and then we need this constant here, which I have to jump over and pull it off of another document real fast. All right. Okay, and let me get that here. All right, so this is another constant that applies to radiation, and it's 5.67 times 10 to the negative 8. All right, so that is just a number that you're given to solve this, and it's relevant to the physics of light radiation. So, light being emitted by something. That larger. There we go. All right. Okay, so that takes care of, and to be clear, I'm talking about the sigma, this little letter that looks like an O with a little tail at the top. And last, we'll just plug in the temperature, which is already in the correct units. So we'll just plug in the temperature in Kelvin right there. So it's going to be 11,000 Kelvin. Make sure to remember to raise it to the 4th power, very, very high power. And that will give us our wattage. How much energy is getting outputted by this star? Okay, so let's plug in those numbers down here. Okay, so I think it would make sense to call, we're not going to be using the wavelength anymore. So I'm going to not call that one lambda, or L rather, and we'll call this one L for luminosity. Like, we could also call it maybe P for power, because this is just, luminosity is just another word for power. Just so I could talk about the wattage of a light bulb, that's what we're going to be getting here, or the wattage of the star. Okay, put in an equal sign. Okay, so 4 pi, 5 times 10 to the 8. Okay, in this example, that would be 500,000 kilometers, to remind you again. Okay, and remember that is squared. Okay, then we'll multiply by the Stefan-Boltzmann constant, just that value 5.67, and then times 10 to the negative 8. All right, this is not one of the fundamental constants, by the way. It's based on other constants, but it's very useful for these radiation equations. 1, 2, 3, and then we'll raise it to the 4th. Got it. Okay, so we did expect a large value, so that looks good. All right, and let's write this down. We have 2.61 times 10 to the 27 watts. That is how much power is getting outputted by the star, okay? We're almost done with this one. Let's go to the last part, which talks about how that energy will reduce per area as the distance from the source gets larger, okay? So that's what E is asking about. It says, what is the intensity, which is also called flux, of the star at its surface? Give your answer in watts per square meter, all right? And then in F, it is, what is the intensity of the star at a distance of 1 AU? Okay, so how would we do that? Okay, so we've got that intensity, which is not power, but instead power per area, is going to be whatever value we got, the luminosity, divided by the surface area of the star, because that would be its power at its surface. The surface area of a star is 4 pi r squared. Okay, so we will be able to plug in those numbers. We'll do that right here. All right, so the luminosity we know to be 2.61 times 10 to the 27 watts. Down here we have 4 pi, my number of 5.0 times 10 to the 8 meters, which is being squared for the surface area of a sphere formula. Again, surface area of a sphere is 4 pi r squared. That and the volume of a sphere are numbers that come up a lot because, well, most objects in the universe are spheres, especially so much of astronomy is focused on studying stars. So, good thing to remember. Okay, so let's go ahead and use our saved value of L and make this calculation. All right, so obviously we'll call this one I for intensity. And that's going to equal our value of L. Got to keep coming back to the keyboard. All right, and then everything in the denominator. 4 pi and then r squared. Okay, so let's open up, just do 5 times 10 to the 8. Okay, remember to square that, and there we go. We have our intensity at the surface. Okay, it's going to be 8 Okay, and now we have to count it. I wish I would do scientific notation even on these smaller values, and I think I could do it in settings. But I'm going to count the numbers here. So 1, 2, 3, 4, 5, 6, 7, 8. So times 10 to the 8. All right. So to go back and write it, 8.30 times 10 to the 8 watts per square meter. So a lot of intensity right on the surface. It's the total output of the star over a much smaller surface area because we haven't gone very far. But what about a planet that is away from this star, right? What about a planet that's orbiting it? It won't get nearly as much energy per square meter, and it will become habitable. You won't just burn up. All right, so we're now going to look at the intensity at some distance. To do this, we have a ratio of I naught, which is some initial intensity, of course, just the value from part E, over some new intensity at a new distance. Well, intensity is proportional to 1 over r squared, so that means we have an r naught squared right there because of that inverse proportionality, the fact that as distance goes up, intensity falls off, all right? In fact, intensity falls off at the rate of the distance being squared. You go twice as far from the star, the intensity of the light, the watts per square meter, has fallen off by a factor of 4. You go 3 times as far, it's fallen off by a factor of 9 because you're squaring the number and putting it in the denominator. And so that means the ratio, it's in the denominator. And this one over here, for the new intensity that we want to find, well, that value is going to be in the numerator because it just has to be, well, the opposite, right? Because of course, we're just dividing by it twice. Now let's solve for that new intensity. So we want to solve for I, and if we cross multiply for that, we'll find that I naught, let's show you some more space here, all right? I is going to equal I naught times, should be R naught squared, R naught squared over R squared. Yep, okay. So what are the values then? So finally, we'll plug those in, which will give us a final reminder on how to deal with the astronomical unit value, all right? So initial intensity, that's 8.30 times 10 to the 8 watts per square meter. The two relevant distances, well, the first distance is just from the center of the star to its surface. So that one would just be the 5.0 times 10 to the 8 meters. The new distance is 1 astronomical unit, at least in the problem you're going to be solving. I'll put in 2 astronomical units, okay? So in my case, I'll take a note of that over here, that R is going to be 2 AU, okay? Well, 1 astronomical unit is 150 million kilometers. So 2 of them would be 300 million kilometers, okay? So 300 million kilometers is how many meters? Well, let's see, right? So we have 2 times 1.5 times 10 to the 8 kilometers, okay? Because 10 to the 8 is hundreds of millions. But then if we want to convert that to meters, we need 3 more zeros, so our 8 would go up to 11. So we'd have 2 times 1.5 times 10 to the 11 meters. Okay, so let's then put in the correct number, just 2 times that I'm using for my example, 3.0 times 10 to the 11, but you'll get, certainly that, remember that 10 to the 11, because yours will not, will be just half of this, meters, and then squared. Okay, I'm going to clear out our little notes here on conversions and just the fact that it's to AU, but hopefully you'll remember that, and it should be obvious by the value of 3. Okay, so the final calculation, let's do it. Okay, so we'll be using our wattage, so that value of 8.30 times 10 to the 8. And yeah, otherwise it's just entering constants, okay, or given numbers. So we'll go ahead and go down. I won't bother to label this one because this is our last calculation that we won't be using it for anything else. Okay, so we'll multiply by I, so we'll start with that. Put in our I. Do some multiplication following it. So, okay, now this is just going to be the fraction part now. So you can see in the numerator, we've got the 5.0 and then times 10 to the 8th. And we're going to be squaring that. Okay, like so. And in the denominator, we have our much larger distance, which is why we're going to get a smaller value for intensity. Okay, so you see how the numbers are going to work out here. We're dividing by a big number squared, much bigger than the numerator. So that's going to give us a very small value of intensity, which we should get because we're much further from the star now. But it's still going to be enough light because it's such a hot star. So I would say enough light to, you wouldn't be in the dark, that's for sure. It might actually be so much light, this planet could be uninhabitable. It could not be in the habitable region of the solar system. Okay, so the final number there is 2,300. All right, and if we just use those numbers significant figures, I guess it actually be 2,310 because that 05 would round up. Okay, and this is watts per square meter. All right, so instead of it being a huge number, a ton of power per area, once we're out, some distance, some orbital distance, some planet orbiting the star, the number becomes much more reasonable. This still will be probably pretty harsh light because it's mostly in the ultraviolet, or it's peaked in the ultraviolet. But in terms of the actual energy or power per area, it's not that bad. Earth, for example, has a intensity level around 1,350 watts per square meter. That's kind of our annual average. So that number goes up in the summer. As high as like 1,800. So you can see this is, kind of right around in that range. So, it wouldn't be unbearably bright, but the ultraviolet would be a problem because we know that is a harmful type of light. Okay, so we'll end the video there. I'm going to make a second video for problem number 2. That one will be shorter. There's not nearly as much to talk about, but we do have to make sure we know how to use our formula for finding distance from an angle or vice versa, and then relate that to another little formula that's going to be solving for an angle as well. Okay, so some talk about converting from one angle to another, but as before, problem number 2 will not use any actual trigonometry. It's basically simplifying it into algebra. Okay, all right, well, thank you so much for watching. I hope this homework help video has been informative.